3D representation. So I think today we will study until this one, 2D, 2.5D, 3D comparison, mesh, point cloud, voxel, and implicit function. Implicit function, I think some of you guys heard NERF. NERF is about implicit function. So we will study implicit function and NERF from next class. And we will study some basic 3D representation, explicit representation today. So this shows comparison between 2D, 2.5D, and 3D. 2D, we cannot change viewpoint. That is so 2D is just a simple single image. It only has X and Y axis. To change viewpoint, we need Z axis, right? We need to lift them to 3D space and then set another camera and then render to the different viewpoint. That is what we learned so far, right? We assuming some perspective projection and then lifting them to using camera parameters and then projection to image space. That is what we learned so far. So 2D cannot change viewpoint. We cannot change viewpoint. 2.5D, it provides some Z-axis, Z values for visible pixels, but there are many invisible pixels in the 2D image, right? So that such kind of invisible pixels, they do not have any data. That is 2.5D. As you can see from this middle video, some pixels, pixels visible from this leftmost 2D image, they have Z value, right? So that if we turn the viewpoint, we can still get colors from such kind of visible pixels, visible points. But invisible points, they do not have pixels. They do not have Z-axis, so that we cannot get data from them. That is about 2.5D, somewhere between 2D and 3D. 2.5D is not very official term, but people usually use such kind of 2.5D representation in practice. And 3D, we can change viewpoint. All points are available, and then we can freely change viewpoint. That is about 3D. Some of you guys, maybe, including me when I was junior, has misunderstanding. I think 2D and 3D, there's nothing about art design. 2D means we cannot change viewpoint. 3D, we can change viewpoint, that's all. Some, including me, when I was junior, I thought that this kind of game is called a 2D game. This kind of called a 3D game. So I thought that this kind of cartoonish design was about 2D, but that is not true. Art design is nothing about 2D and 3D, as I said. If we can change viewpoint in this game is 3D game. So only about viewpoint change, nothing about art design. Cartoonish design, photorealistic design, nothing matter. Only difference is that we can change viewpoint or not. And 2D, 2D and 3D, the only difference is Z-axis, right? But the only difference is Z-axis, but many things are actually, such kind of small difference make huge difference. The 2D is image is a rectangle shaped tensor, right? Image, we have image, Y-axis, X-axis, always a rectangle shaped tensor. Each pixel has intensity of RGB channels, right? So we have R channel, G channel, B channel, and each pixel has 0 to 255 intensity. That's the typical image, right? But how maybe we can extend this to 3D case. So maybe we can. So the extension of rectangle to 3D is a cubic, right? So we can make a cubic for R channel, another cubic for G channel, another cubic for B channel. Maybe there's a simple extension of rectangle image shape tensor to the 3D shape. Actually, that is the volume. We call this such kind of data representation as a volume. We will study soon. And then for each pixel, it has intensity of RGB channels. But the difference is that there can be empty voxels. That is the biggest difference between 2D image and 3D case. Images, each pixel might have different depths. So that if we take camera, there can be empty space in 3D, but 3D points whose depth is, larger than other pixels can be projected to the 2D shape, right? So that we always have fully fully occupied images. We always have fully occupied images. There is no empty pixels, right? But I mean 3D space, for example, if I have a bottle here, this space is empty, right? This space is empty. We have many empty space. So that we need to define empty space. That is the biggest difference. So how can we define empty space? Maybe we can use occupancy value as well, so that we can define R volume, R cubic, G cubic, and B cubic, and then some binary as well, occupancy, so that if it is empty, then we can set here as 0, binary. If it is empty, then we can set this occupancy as a 0. If it's occupied, then we can set this occupied as a 1, so that we can make a 4-dimensional, 4 volumes to define some space, 3D space. RGB as an intensity, and occupancy as a binary, whether this voxel is occupied or empty, so that we can introduce this kind of 4 volumes to explain 3D space. We can, but the limitation, weakness is that too huge memory requirement. Image, I mean, these days we have 4K images, right? 4K means 4K, 4,000 pixels, and typically 2,000 pixels, or this kind of, I mean, but if we need to get enough resolution, then we need to introduce additional 4K. I mean, here 4K, no, here height is 4K, width is 2K, and depth should be 4K. Then, I mean, we need huge amount of memory, right? We introduce this memory usage of this one is 4K times higher than this one, right? Two huge memory requirements. So that this kind of simple extension is still widely used, but it is not optimal in many cases. So that in 2D case, we only have images, right? But I mean 3D, depending on your task, depending on your preference, we use more than one representations. So that we have point cloud, voxel, polygon mesh, or implicit function to define 3D data. So that is the reason. So unlike 2D case, there are several representations for the 3D case: point cloud, voxel, mesh, implicit function. As I said, the major reason is that volume is the direct extension of image. As I said, we can define R volume, G volume, B volume, occupancy volume. It is, I mean, mathematically it is enough. We can fully define 3D space with 4 volumes, but in practice, it takes too much memory, so that only using volume, it is not very good. So that is the primary reason why we introduce more than one representation in 3D case, although we have only one representation in 2D. So we will start with mesh, or triangle mesh, polygon, or just mesh. They are the same. So we present 3D shape as a set of triangle. The reason, I mean, we can maybe use square, but why we need triangle? Because mathematically 3 points define one plane, right? Only 3 points is the requirement to define a single plane. So that is the reason why we need triangle. We define triangle as the basic component of triangle mesh. And we're only interested in surface of object. So this shows the triangle mesh. Represent a 3D shape as a set of triangle and set of points. So vertex, there are 2 components, vertices and faces. Vertex is set of points in 3D space. This one, these white circles are just vertices, vertex. And face, instead of triangle over the vertices, we need to define which vertices, which vertices make a single triangle. So let's say this is the V1, V2, V3, V4, V5, anything. So that we know that V1, V2, V3 makes this triangle plane, right? and V3, V4, V5. Also make this triangle, right? So we need to define vertices and at the same time face. Face is deciding which set of vertices make a single triangle. So we need two things, vertices and faces. This is actually almost the same as the graph structure. I'm not sure you learned graph structure in algorithm. Graph, we have node and edge, right? So we can interpret mesh as just a graph, node and edge. Actually, these are just node. The white circles are just node, and these lines are just edge. We can interpret mesh as just a graph structure. Anyway, mesh, the good point is the standard representation for graphics. It is used in everywhere, like all computer graphics, movie, game, TV show, all the things are based on mesh. Most of them are based on mesh. And explicitly represents 3D surface. So in the previous slide, I introduced some empty space with volume, right? But this surface mesh or triangle mesh, it does not define any empty space. Just we have a surface, right? We only define surface. We are not interested in empty space. We are not interested in inside of this object. We only define surface with triangle mesh. That is how triangle mesh defining 3D object. So vertices, they are only on the surface of some object. The vertices are not on the empty space. And another good point is adaptivity. You can represent flat surfaces very efficiently, can allocate more faces to areas with fine details. So for example, let's say we have this huge desk, right? This huge desk, let's say I have an iPad here. iPad, the front part of iPad, it just needs two triangle, right? Huge triangle, that's all, right? We need just how many points? 1, 2, 3, 4. We need 4 vertices and 2 faces. It's enough to define the front panel of iPad, right? Very efficient. Flat surface, very efficient. But in some, not non-flat surfaces, like a curved surface, we need to allocate more triangle faces to curved faces, so that flat surface, we can represent flat surface very efficiently. At the same time, allocate more faces to areas with fine details, so that we can adaptively allocate triangle faces. That is the good point of triangle mesh. So that triangle mesh is very efficient, actually. It is good for real-time demonstration and required very small amount of memory. So mesh is very efficient. So that is the reason why mesh is widely used in real-time applications like a video game. And another good point is that it can attach data on vertices, interpolate over the whole surface, RGB colors, texture coordinates, normal vectors. So for example, let's say there's a dolphin here. So that let's say we have this triangle face here, and then let's say we know color 1, color 2, color 3. We know colors of each vertex. Then how can we get colors of some points inside of triangle? How can we get them? I'm not sure you learned pericentric coordinates. All the points inside the triangle can be interpolated with, C1, C2, C3. Any arbitrary point inside the triangle can be obtained by linear interpolation of these 3 values. That is about pericentric coordinates. So anyway, we can interpolate colors of each vertex to get colors of any points on the surface, so that we do not need to define very dense points. Although we have these 3 points, we can get colors of all points inside the triangle using pericentric coordinates. So that makes very efficient. We do not need very dense vertices because of this pericentric coordinate representation. So that is what it is saying. You can attach data. We can attach like RGB colors or texture coordinates, normal vectors for each vertex. And then then we can interpolate interpolate such kind of attached data for points on the triangle face using barycentric coordinates. We will learn barycentric coordinates soon. Anyway, that is also a good point of surface mesh. Very efficient. At the same time, we can get dense values by interpolating inside a triangle. But the drawback is that non-trivial to process with neural network. Also, we will study soon. So this is called topology of mesh. So as I said, mesh, we need to define vertices and triangle face, right? Vertex is the shape is n by 3. N is number of vertices. X, Y, Z coordinate of each vertex. That is just the vertices. And face, vertex index of each triangle face. As I said here. Here, we need to define which vertex make each triangle, right? So that we need two things to define mesh. Vertices, X, Y, Z coordinate of each vertex. At the same time, we need to define triangle face with vertex index. That is the basic components of triangle mesh. And only represent surface. As I said, mesh only interested in surface of object. It is not interested in exterior or interior region of object. So this shows topology, a little bit mathematical figure. I mean, so for example, if we have this kind of sphere, we cannot make this kind of donut shape geometry out of this sphere shape. They belong to different topology. You can imagine how can we cannot get this one. We can make a hole in. Maybe we can make a hole here, but as I said, interior of sphere there's no vertices, so that we cannot make this kind of interior part surfaces with sphere. So that mesh topology, it is similar to mathematical topology. This shows topology of mesh, and then, as I said, we only interested in surface of mesh. This shows the visualization of interior space of human mesh. We can use visualizer, and then you can see there's a empty. All things are empty. Just interested in surface of object. Interior, exterior, we're not interested in. Just surface of object. And we can use single topology to represent similar object. So for example, so these meshes are all from the same topology. So topology, as I said, means vertex and face. All these meshes are from the same topology. Same number of vertices, same number of triangle face. Each triangle face consists of the same triangle, same vertex. So that we can, for example, if we're only interested in human, then we can use single topology to represent human. For example, the 0th vertex always represent eyeball, and 100 vertex always represent nose. Then when we design some triangle mesh, then 0th vertex can always have eyeball color. So this kind of vertex position could be vary. Depending on the human pose, the vertex position, this n times 3 might change, but we always need to assign eyeball color to 0th vertex if we only use a single topology to represent similar object. So that makes preparing assets very easy, right? And that is the reason why 3D meshes are widely used in industrial research, because animation and motion capture is really easy, straightforward when we use mesh. I think this might be a little bit not easy to take. So let's say we have 200 vertices, x, y, z. So the position of x, y, z, the value of x, y, z, which means the position of each vertex, could be different. Depending on the human pose, the x, y, z value could be different. But the 0th vertex, this one, it always represents eyeball vertex. Here, eyeball, this one, eyeball vertex. Or this one, this 100th vertex always represent nose vertex. So that when preparing these meshes, when let's say we are interested in making some animation, and then we need to assign color for each vertex, then this human might move, right? This human might move, but we always for the zeroth vertex, we always need to just assign eyeball color, like black, brown, or blue, any eyeball color depending on human. We can assign the same eyeball color regardless of XYZ changes. So that makes animation and preparation much easier than voxel and point cloud. And another good point of triangle mesh is that it has surface. Surface means we can get normals. This is albedo, normal map, and related image. We can get normal for all points on the triangle face. And normal is, as I think I introduced this one at the very early part of this course. For the lighting means let me turn on some light, then my color changes, right? There's a shadow and color change. As you can see here, this is light, changes, right? For the lighting, this is rendering equation, and mathematically, normal vector is necessary for relighting. So based on physics, we can naturally incorporate lighting in triangle mesh, so that it's very easy to incorporate lighting in the triangle mesh. That is another reason why all the animation, all the computer graphics are based on mesh in industry and research with mesh. And texture. So this is, I'm not sure, maybe some of you guys might have seen this kind of UV map. Let's say we are 3D artists and we have some character here, we have some, or object, we have some 3D scene, and then we need to draw something, right? We need to assign some colors. We might want to add some funny logos or funny colors on the character or scene. That we need to draw something, right? But how can we draw? Maybe we can draw something on 3D space, but that is actually not very good. Maybe in practice, we humans are not familiar with drawing something on 3D space, right? How can we draw something in 3D space? It's not very easy. We are familiar with drawing something on 2D plane. And also in 3D space, like this example, this woman is holding a baby and her elbow might not be visible, so that we can't draw something on her elbow, right? So that makes, depending on 3D pose or 3D configuration, there can be invisible points, so that drawing something on invisible point is, basically not very easy. So that people invented a smart way to draw something on triangle mesh. That is the UV map. So UV is similar to XY. So we have 3D XYZ, and then we can just unwrap it. Unwrap the triangle full 3D surface to 2D space. So that is the UV map. So so let's say my head is here. I open my head and then make a flat picture of my head in the UV space. This XY is the UV space. This one, UV space. And then I can draw something on UV space. That is what 3D artists are doing to add some textures on the 3D mesh. Maybe a 3D artist can assign my skin color or my eye color, hair color, or some jacket color, anything. 3D artists can draw, add textures on the UV map. That is how we can get colored meshes. And this is called UV map. Of course, we can add colors on the UV map, but we can do many things in UV map. We can, maybe we can add some normal maps in UV map. We can add some lightings in UV map. We can do all the stuff in UV map because we have a correspondence between 3D and UV space. So here, at the first, I introduced only 2 components in mesh topology, but actually there are 4. Unfortunately, there are 4 components in mesh topology here, additional one. So these are 3D, it's 3D and UV. 3D is the same as I introduced, vertex coordinates in a 3D space, XYZ coordinate of each vertex, and triangle face, vertex index, which vertex make this triangle, that is vertex index. And triangle face in UV map, it is same number as triangle face here, F is the same. So one-to-one, there's a one-to-one matching. So this is a F3, and this is a F3. This one is this one, this one is this one. The one-to-one matching means this triangle face means this triangle face. In UV space, for example, let's say there's a triangle on her body like this, then this one. This triangle face is this triangle face. One-to-one matching. There's a one-to-one matching between triangle face in the 3D space and one-to-one matching in triangle face in UV space. But as you can see, there's a small prime here. It is different, right? V and V prime are different. V and V prime are different. So number of vertices in 3D, that is V. Number of vertices in UV, that is V prime, could be different. Because you can think about the seam area. Let's say I open my head. Let's say my head is here, and I open my head like this. Then this seam area, originally in 3D space, this one has a single point, right? But when I open this one, then there is a multiple points, right? These 2 points actually belong to the same point, the 3D space. But in UV space, as we unwrap 3D to the 2D space, there can be multiple UV points, which actually meaning the same point, the 3D space. So the number of vertices in UV map is different from number of vertices in 3D space. The triangle face is the same. And to render triangle, let's say we design all those stuff. We design UV map, we have 3D geometry, we have all the things. Now we are ready to render, we are ready to get images, we are ready to render. Then how can we get rendered images out of triangle mesh? There are 3 stages. The first one is called rasterization. Let's say we have triangle face, and then we have camera. Then rasterization means we project triangle to the screen space, considering visibility. Let's say this is your eyes are camera, and then this one, this zero, this character might not be visible from your camera, right? Because the triangle, we have a visibility check, and then this triangle are not included in your rasterization because this area is not visible. So we have visibility test, and then we project only visible triangle face to screen space, and the output of rasterization is a rendered triangle face. Each value means triangle face index. Triangle face index. We have a f number of triangle face, right? So each pixel has a 0 to f minus 1. Maybe just a triangle face index. Which triangle face is visible from this pixel? That is the output of rasterization. And then barycentric coordinates. So as I said, this is a barycentric coordinate. If we have a some value A, B, C, then some point inside of triangle can be interpolated with barycentric coordinate system. And then, so the output of triangle rasterization is a triangle face index in the image. It's just the image, height and width image. Each pixel has a triangle face. At the same time, barycentric coordinate. Then, we can specify some triangle face, and then using barycentric coordinate, we can specify exact location inside of the triangle face, right? So that is the output of rasterization. And then texturing. So we now rasterized triangle face to the input image space, and then now it's ready. It's time to get color from UV map. We have color here, right? We have UV map color, and then we use triangle face index. This one triangle face index. As I said, the triangle face index can be used interchangeably. We can use the triangle face. Let's say this pixel has a triangle face of 100. Then we can get color by taking 100 elements in this UV map, triangle face and UV map, and then this triangle face maybe this one. Then we can get color out of this triangle, right? So given triangle face index from rasterization, we can visit UV map to get color, right? That is how we can get color from combination of 3D geometry and UV map. That is the texturing. So rasterization is just simply projecting triangle mesh to the screen space considering visibility of each triangle. And then texturing is based on the output of rasterization, which are triangle face index and barycentric coordinates. We can we can get colors from UV map, right? And lighting is a little bit advanced than computer graphics stuff, so I will not cover detail. Just based on normal vectors, rendered normal map, and then using some BRDF, we can get lighting. But we will primarily focus on this one, rasterization and texturing. Lighting is a little bit computer graphics. This might be a little bit confusing, but so you need to understand the relationship between XYZ 3D and UV stuff. And this one is, I think you can visit this slide, I think. So we have a 3D stuff in XYZ space, and at the same time, we have something in UV space, and then they are, this F is the same. So we can make this one as a connection between 3D and UV. And each triangle face, we can visit here, we can visit here, right? So we can use this triangle face index as a connection or bridge between 3D and UV. And then once we figure out triangle face, we can visit, if we want to get 3D coordinate, then we can visit here. If we want to get a color, then we can visit here. So triangle face index can be used interchangeably in 3D and UV. So that is some bridge between 3D and UV. And that is the reason why we get triangle face index in rasterization, because triangle face index is the bridge between 3D and UV. And the barycentric coordinate, it tells us exact location inside of triangle, right? So based on the output of rasterization, we can visit UV map to get color of each vertex using just interpolation, and then all pixels have colors, right? All rasterized pixels have colors. That is what is happening in mesh-based rendering. In movie, video game, animation, all the things are the same. Just rasterize and then get color from UV map. That becomes rendered image. And this one, as I said, limitation of triangle mesh is that it is not trivial to use in neural network if topology is not fixed. Here, let's recap topology. Topology is a number of vertex. Vertex. Number of vertex and face. Triangle face. So number of vertex and number of triangle face and definition of each triangle face is not fixed. Then incorporating triangle mesh in neural network is not very easy. Let's say we're interested in image to 3D mesh reconstruction. Then how can we define output layer? So this is the typical neural network for the image classification. As you can see, this output layer, fully connected layer, requires a predefined number of classes, right? Because we need to define learnable weight. Learnable weight here. We need to convert some features to the number of classes using this predefined weight, right? But if the number of vertex, if the number of triangle face is the triangle face is not fixed. Let's say the number of vertex is not fixed. Number of vertex can vary. Then we cannot define some learnable parameters in neural network. The incorporating triangle mesh in neural network, because the topology cannot be unique one, then it is not trivial to incorporating triangle mesh in neural network. So we can divide cases, like if we want arbitrary object or scene, then as I said, actually mesh is not best option, as neural network assumes predefined number and order of outputs, usually. So that in this case, maybe we can assume a certain topology and deform it. But if we're interested in a single object, for example, human, then you can use mesh with a fixed topology, and mesh is a good option. So here, arbitrarily object. If we're into arbitrarily object, then we assume this one. This is topology with genus equals to 0, right? We assume some topology of mesh, let's say ellipsoid or sphere, and then we can just deform the sphere by moving some vertices on the sphere, right? That is what is happening in arbitrary object image to 3D mesh reconstruction. Because we cannot introduce, neural network requires fixed number of outputs, then there's no way to incorporate the arbitrary topology meshes in the inside of mesh. So that early works tries to use this kind of ellipse or sphere as a basic topology of the mesh and then just deform each vertices so that they can reconstruct this kind of 3D mesh. Well, obviously, this method cannot recover donut shape, right? The donut has different topology. There is no way to deform this ellipsoid mesh to donut mesh. So this is always limited by topology of given mesh. But human, there are many human-related mesh models like SMPLX. So the human naked human body might have some common topology, right? Usually we have 2 arms, 2 legs, 10 fingers. We have 2 eyes, so that we can define some fixed unique topology that can represent most humans. But still that is limited to naked body. That means it cannot be used for cloth, representing cloth. T-shirt, open jacket has different topology, right? T-shirt, it is closed, but open jacket, there is a topology difference. Or pants and skirts, they also belong to different topology. So mesh is good. The conclusion is the mesh is good, but incorporating mesh in the neural network is not very trivial. These days, there are many advances in algorithm side, and then now meshes or other representation can be used in neural network, but incorporating mesh in the neural network is not very easy. And industry, as I said, it's used everywhere. Any computer graphics in movie and game, animation. 3D artists make 3D mesh assets. Like some assets share same topology. Naked human body, they use the same mesh. And the clothes, as I said, they use different topology. And then for the color, they add textures on the UV map. And the lighting, based on normal vectors, physically based rendering, PBR. And Unreal Engine is a linear physics-based engine, or maybe we can use their customized engine. Anyway, so mesh is used everywhere, very widely used, but not universal solution. As I said, incorporating in your network is not very easy. It cannot represent object with different topology. That is limitation of mesh. It's good about mesh. No, anything is unclear. So the student asks, how can the output of the neural network can deform this given template mesh? So we can output translation vector for each vertex, right? We have a predefined number of vertices, right? Then we can estimate offset for each vertex, then we can change the position of this vertex to this position of vertex to this position, to this position. So we always have a fixed number of vertices, so that the network just simply estimate translation offset for each vertex. So in this way, we can add such kind of offset to this ellipsoid mesh, so that we can get deformed mesh. So connectivity is fixed. So we have a ellipsoid mesh at the basic template. So we have 2 things in topology, right? Vertex and face. This is fixed. We do not change this one because we assume fixed topology. So that this one is fixed. Well, we change only this one, by adding translation vector to the vertices, initial sphere ellipsoid mesh. You can change. So that is the reason why I said it is bounded by genius 0 mesh. If we can change triangle face, then we can change topology so that we can represent donut shaped meshes from this ellipsoid mesh as we are assuming fixed topology, because the number of vertices, the triangle face needs to be constant in neural network, because neural network needs to be, by nature, it assumes some predefined data type. So that is the limitation of this kind of pipeline. 해결됐나요 혹시? Anything is unclear? Okay. and point cloud. So I think maybe many of you are already familiar with point cloud because the assignment 2 was the point cloud. We perform structure from motion, and the output is point cloud. Represent shape as a set of p points in 3D space. So a little bit similar to mesh, but we only have point. There's no triangle face, just a point. So it can represent fine structure without huge number of points, but it doesn't explicitly represent the surface. Doesn't explicitly surface of the shape. So extracting mesh for rendering or other application require post-processing. So point cloud itself is not very good representation for rendering, image rendering, because we do not have surface. So we need to do some post-processing based on point cloud to get mesh, and then mesh is used for image rendering. This is the visualization of point cloud. As you can see, there is only point, just a literal point cloud. There are many points like cloud, and there's no triangle mesh. And I think many of you guys may have seen this kind of picture in autonomous driving community. So LiDAR is a name of sensor or depth sensor. I think these days many mobile phone has depth sensors. So point cloud is powered by LiDAR and depth sensors. LiDAR is maybe, I think I heard Tesla is just using RGB images, but many autonomous driving cars are using LiDAR as a primary sensor. And these are visualized data collected from LiDAR sensor or depth map. We have depth map. As I introduced in previous class, depth map is each pixel has the depth value, and then we can just lift them to the point cloud. So LiDAR and depth sensor measure distance by illuminating a target with laser light and analyzing reflected pulses. So simply saying, you shoot a ray, and then there's a reflected ray comes to the sensor, and the measure time, as we know speed of light, then we can get distance. That is the basic principle of LiDAR or depth sensors. It is called time of flight, often the time of flight sensor. So it might be a little bit noisy because there might be some small things on the air, like there can be some small dirt on the air. Then if we shoot a ray, then the ray can be reflected from dirt, and then we might have some noisy observation. And point cloud is the only representation that can be measured with sensors. As I said, mesh is obtained from point cloud. We cannot get mesh from sensor. There is no sensor that directly measure meshes. There is no sensor that directly measure volume. Point cloud is the only representation that can be measured with sensors. So if we have sensor, then we get point cloud from sensor, and then we can convert that point cloud to mesh or volume depending on your preference. And as I said, it is not suitable for photorealistic rendering, as some pixels could be empty. You can see here, we have depth map, and then we slightly change viewpoint, but there can be many, including here, there are many empty space, right? With LiDAR, we shoot a ray, and then we just get a reflected point. So some point behind the reflected surface, we cannot get observation, so that there are many empty pixels. So that photorealistic rendering is not very suitable for point cloud. So that is the reason why we convert point cloud to mesh and then do rendering. And the famous 3D Gaussian splatting is not perfectly based on point cloud, but it is somehow based on point cloud representation. Combination of point cloud representation and splatting. We will study it later. And point cloud, number of points vary. The order of points vary. A little bit tricky to handle with deep neural network. As I said, same as mesh. So neural network, we need to predefine number of points, but point cloud, number of points can vary. So how can we define neighbor points? Definition of neighbor point necessary to understand local global context of a point. In triangle mesh, we have a triangle mesh, right? Triangle face, so that vertices belong to the same triangle face might be neighbor of that vertex. But on point cloud, we do not have triangle face, so that it is a little bit tricky to define neighbor of each point. For example, image, we have this kind of grid structure image, right? So the neighbor of this pixel are this one, right? or volume. Volume is a simple extension so that we can choose the neighbor voxels. Mesh, vertex on the same triangle face. We can consider them as a neighbor of that vertex. But the point cloud is we do not define connectivity between points. It is a little bit tricky to define neighbor of the point. So that is the reason why many point cloud processing neural network are defined based on this kind of architecture. This is a point net. I think, of course, these days there are many advanced neural network and algorithms, but early days, let's say we have input point cloud, we run MLP on each point. MLP is shared for each point. And then we have max pooling and then fully connected layer. So the reason is that we want to process point cloud as a set. Mathematically, the definition of set is that it is not dependent on the order of data, right? Order should not matter. So the neural network for point cloud processing, they are designed to be not considering order of points. I mean, as I said, run MLP each point, and MLP is shared for all points, and then we have max pool, so that we aggregate points or point features to the single pooled vector here. So we do not have P now, right? We no longer have P here. So just aggregating points features to a single pooled vector and then do something. By nature, point cloud, as I said, the number of points vary, the order of points vary, so that it is not easy to define neighbor between points, so that the neural network for point cloud processing simply take all the point features into a single vector and then just do something. Okay, point cloud is okay, no problem. Anything unclear? Okay. And voxel, I briefly introduced voxel at the early part of this slide. It just represents a shape with cubic grid of occupancies. So it's a simple extension of image. We can define 3 or 4 volumes to get RGB or occupancy as well. So conceptually very simple, just a 3D grid, that's all. Very similar to image. We are already very familiar with image. So conceptually very simple. But as I said, it high spatial resolution to capture fine structures. X, Y is not enough. We need Z-axis, and then memory requirement becomes very huge. So that scaling to high resolution is non-trivial. As you can see, this image and this voxelized volume, I don't think they have this fine detail is not very good. A lot of very discrete visualization, so that it is not very suitable for fine-grained structure. And these are just, you can think like a 3D voxel like a Lego or Minecraft. They are, actual implementation of Minecraft might be based on mesh, but visualized Minecraft visualization is based on voxel-looking visualization, right? That's the 3D grid. There are many 3D grid in Lego or Minecraft, right? And define 3D space, and each voxel has intensity, as I said. RGB intensity, and binary voxel has occupancy. It is called occupancy grid. Occupied is 1, empty is 0. We can define binary voxel. And it is actually very different from mesh and point cloud. Mesh and point cloud, each vertex or points are defined only on object, right? They are not interested in empty exterior, interior region of the object, only interested in object surface. But on voxel, it is space-centric representation. It first defines space, and then if the voxel is occupied or has some intensity, then we fill them. If it is not, it's just empty, we can just set them as empty. So we first define voxel, we need to first define space and then fill voxels. But the mesh and point cloud, they do not define space. They just define points on the surface, right? So the voxel is a space-centric implementation, a little bit different. Point cloud and mesh are point-centric implementation because they are only interested in surface of object. And a simple extension of 2D image that define 2D space and each pixel's RGB intensity. For image, all pixels always occupied at 3D points with different depths can be projected to a pixel position. For voxels, some voxels could be empty. This is actually my first publication actually based on voxel. So I actually very liked voxel. when I was student. My first publication was voxel, and 3D, it's based on 3D CNN, and the 3D CNN is the most straightforward way for voxels in neural network. Because, I mean, in image processing, we use 2D convolutional neural network, right? Then in voxel is simple extension of image. Then we can use 3D convolutional neural network. 3D convolutional neural network, 2D, in case 2D, we have 2D kernel, K, and the dimensional, the number of parameter in 2D kernel is that K times C in, C out. That is 2D, right? Then 3D case, we have one more axis here. So that K times C in, C out. That is number parameter in 3D convolution. So very similar to image processing, just the 2D convolution or 3D convolution. The only difference is that we have additional z-axis. And voxel strength is topology free. It is not constrained by topology. Mesh, although it is widely used, as I said, it is constrained to specific topology. Mesh of sphere cannot be used to represent mesh of donut shape, right? Because of topology constraint. But the voxel, it is not constrained by specific topology. So that despite the computational inefficiency, it is widely used in this kind of fire, steam, or hair, this kind of thing. Because, actually, it is not natural to represent fire with surfaces, and also this kind of defining topology of fire, defining topology of steam is not very trivial, right? So this kind of some steam or fire are rendered in volumetric rendering. In physics engine, you can see volumetric rendering option, and this kind of fire or steam are rendered in volumetric way. And this shows the memory usage of voxel. As you can see, 1K by 1K by 1K voxel in floating 32 number, it already takes 4 gigabytes. Imagine you have a single image. Maybe a single image might take few megabytes, right? Although it is 4K resolution, it might take few megabytes. But 1K, not 4K, just 1K voxel take 4 gigabytes of a memory, just a single voxel. That is huge, very inefficient. So people invented some smart way to handle this kind of scalability issue using octtree, or there are many. So first, defining some coarse level voxels, and then adding some fine-grained stuff based octtree data structure. And I heard that in medical image processing research area, people actively using voxels to handle MRI data. So MRI, I'm not sure, I'm not very familiar with this kind of MRI data, but I heard that MRI is consecutive image along the human body, so that people still widely using voxel to handle MRI data. Okay, and anything is unclear about the voxel? So let's finish after checking the attendance. Anything okay about the voxel? No problem? Okay, let's finish. Thank you.